We were talking about the structure of the atom. Is that right? We were talking about the structure of the atom and we said, oh, Bohr said that electrons go around like planets. Now, it's not like, oh, I see planets around the sun, so I'm going to propose it. It wasn't like that. All right? Bohr's people believed in the Bohr model of the atom because when he looked at the spectrum of the hydrogen gas, all right, he was able to give us an equation and he was able to calculate the wavelength of the light that came out. Because he was able to calculate and it matched when I took the spectrum. Does that make sense? When I looked at the spectrum and it matched with the map, people were like, yes, you are right. This is how the orbits look around the nucleus, and we can understand that these transitions take place. They are in the visible region of the spectrum. These we see with other sophisticated instruments, we see them in the ultraviolet region. Because he was able to give us the math behind it, we believed in Bohr's model. So what was the equation? The equation is known as the Rydberg equation. So for every transition from whichever higher energy level to whichever lower energy level, the energy difference is given by this equation. All right? Wherein final is the final energy state to which it arrives, and an initial is whichever initial state from which it originates. Does that make sense? Okay? And these are whole numbers. They are integers. All right? Now, this model correctly fits the quantized energy levels of hydrogen, and it lets us know why only certain allowed circular orbits are there for the electron. So if you look at an atom based on Bohr model, you will not find an electron anywhere in between. Is that right? It's only found in certain circular orbits. Now, this is another interesting aspect that you should know, which I didn't discuss before. So please know that for an electron that is completely outside the nucleus, all right, that is not at all attracted by the nucleus, the energy is equal to 0. When it's far away from the nucleus, the energy that an electron has is 0. And we said the energy decreases as it moves closer and closer to the nucleus. It has more and more energy as it moves away from the nucleus. Or in other words, as it gets closer to the nucleus, the energy levels become more negative. Does that make sense? So for a faraway electron, I could say this is like minus 20 or something. Is that right? But then for something that's closer, it would be like minus 50 or something. Does that make sense? Do you understand it? It becomes more and more negative. As the electron is brought closer to the nucleus, the energy is released from the system and it becomes more negative related to the zero energy state. Does that make sense? Okay, moving on. So here is the picture. When it moves to n equals 3, it's in the IR, this is in the visible region, that is in the ultraviolet region. Do you all see that? Okay? Now, the very first equation, say the electron Vinci drew something on you?
Did not draw anything on his map.
I guess not. I don't know.
Okay.
I think he's like just seeing things out. There's nothing here.
Why is the class being distracted?
I don't know. He was distracted. He was like, I'll know what else he's doing. I don't know. He was distracted.
Okay, can I have 2 bars, not 2 bars. One of you move to the other table with Garrett. Yeah, it helps. I can't believe it. You know, I really don't like to control student behavior. Because I think kids are capable of controlling their behavior in class, so that learning takes place, right, Brandon? If learning is not taking place, then I will tell you how to behave. And that is not a good thing to happen. Alright? If I take away your liberty, and you're right, don't use the cell phone in class. I think that's not a nice thing for a teacher to say to a student. It tells me that the student is really immature. Get off the cell phone. At your age, really? Do you need this from a teacher? I'm told at TJ there is no bell. Kids don't ask for restroom breaks. Why? Because they want to be treated with dignity. Alright? They believe I'm responsible for my learning. You don't tell me when I have to visit the restroom. You don't tell me when I have to be in class and when I have not got to not be in class. And I think that is fair argument. When it comes to my honors class, I really don't give seating charts. I don't make seating charts. I really don't closely monitor whether you're using your cell phone. I don't look at and see, oh, are you chit-chatting with a friend next to you? If you ask for a restroom break, I'm like, leave the class. Don't disturb me. All right? It is on you. Don't let me take control of your behavior. And all this is getting recorded. Okay, that's why I don't like recording lectures. Anyway. Okay. So drawing something on somebody's back when a lecture is going on, really seriously. Are we in middle school or elementary school? Okay. Can I continue to teach? Thank you. Okay. So we're going to get into the Rydberg equation and the calculations that go with it. All right. I purposefully typed out a whole set of calculations so that you stay with me and you understand the problem, and we will try to do one of our own. All right. So the electron is making a transition from n equals 5 to n equals 2. What they want you to calculate is what is the wavelength of the resulting light that comes out when it makes the transition from n equals 5 to n equals 2. What will be the wavelength? So it does come down. It comes down in the form of light. It releases it. What is the wavelength of that light which is released? This was Bohr's calculation. All right? So here is the Rydberg equation, right? And in the Rydberg equation, you have to understand what is the final level to which it is coming. It's coming to n equals 2. It's starting at n equals 5. So let's substitute. That's the final. 2 squared. 5 squared is the initial. You plug it into your calculator, you get the energy difference between the two energy levels. Yes or no? Once you get the energy difference, you know the energy. Can you calculate the wavelength? Did we just do this on the warm-up? E equals hc by lambda. Can you flip lambda and delta E? And then you go on, you substitute in the equation, all right? And once you substitute, you will get the answer in meters, and you convert it to nanometers. Once you convert it, you know it's 434 nanometers, and it means, comparing this with the electromagnetic table, we find that this is the blue light that's given out by the hydrogen spectrum. Does that make sense? Now, I want my students to calculate when it goes from n equals 4 to n equals 2. Do you want me to do it with you, or would you like to do it yourself? Do it with you, all right? Slowly, all right? So let's write down the Rydberg equation. What is the Rydberg equation? Delta E equals negative 2178 times 10 to the negative 18 joules. By the way, the equation will be given to you on a test. You don't have to memorize the equation. All right? And final squared minus 1 by n initial squared. Is that right? Okay. So we are going to do the transition n is equal to 4 to n is equal to 2. So let's plug it into the equation. 178 times 10 to the negative 18 joules. What is my final state? 2 squared, which is what? 4, 1 by 4, minus, that's 4 squared, which is 1 by 16. Alright? Can you now put this number in your calculator and it will give you an answer. Alright?
That's what you're talking about. Adding four. From the question. That's the question.
Oh, I don't use this calculator. I'll do this one. So what did you get? Negative 4.08. Okay, 084. Okay, times 10 to the negative 19 joules. Yeah, it's already negative 18 there. Right? Are you getting this number as you plug it into your calculator? Okay. So now we know the energy. From energy, what are we going to calculate? The wavelength. Is that right? So what is the relationship? We know delta E equals hc by lambda. Do we know that?
Yes.
All right. So can I interchange these two? And what does it become? Lambda equals hc by delta E. Now, this delta E here is negative. Yes or no?
Yes.
Even though it is negative, I will not consider it when I'm solving for my wavelength because that is energy released. Energy absorbed is always positive. Energy released is always negative. So because it is released, it shows me the negative side. I really don't care about it when I solve for my wavelength. Is that understood? So now I'm going to substitute my values. What is my Planck's constant? 6.63 according to you, is that right? Negative 34 joules second times my speed of light is 10 to the 8 meters per second. Alright? Divided by my energy, which is 4.084 times 10 to the negative 19. What do you think my final answer will be in? Joules, right? So it will be in what units? It will be in meters. Okay? So if I plug this number 6.63
Well, I just like,
what do you get, guys? No negative. That negative is dropped. If we talk about it not math, it doesn't matter when I calculate wavelength. So what is it? 4.87. Let's just keep 4.87 times 10 to the negative 7. This is in what units? Meters. Now, if I bother to convert it into nanometers, all right, this is getting multiplied by what number? This is negative 7 and 9. It's getting multiplied by 100. Can I say it's 487 nanometers? Right? So the wavelength of light released is 487 nanometers. Do you all see that? Now, if you go back, if it's 487, what light do you think is given out? Green light. All right? So you will be able to see a light that is green because of this transmission. Does that make sense?
Yes.
So maybe you can do one at home, all right? Now, I think I gave you a problem, all right? Let me